May 10, 1940. Squadron Leader Harold Bird-Wilson pushed his Supermarine Spitfire into a steep dive above the French countryside near Sedan. Below him, a formation of German Messerschmitt Bf 109s banked hard, their pilots confident, aggressive. Bird-Wilson had altitude. He had speed. He had the angle. What he didn't have was an engine that would keep running. At 4,000 feet, he rolled inverted and pulled the stick forward. Negative gravity. The horizon flipped. His stomach lifted. And then silence. The Rolls-Royce Merlin engine coughed once, sputtered, and died. No power. No thrust. Just the whistle of wind over the canopy and the sick certainty that he was about to fall out of the sky while German fighters scattered beneath him like startled fish. Bird-Wilson leveled out. The engine caught again, coughed back to life. He climbed away, heart hammering, hands shaking on the controls. The Germans were gone. He was alive. But the problem remained. Every Spitfire pilot in fighter command knew it. Every Hurricane pilot had felt it. When you pushed into a dive to pursue an enemy aircraft, when you needed speed and power most desperately, the Merlin engine quit. And the Germans never had that problem. The Luftwaffe's Messerschmitt Bf 109 used direct fuel injection. Dive, climb, roll inverted, it didn't matter. The fuel kept flowing. The engine kept running. German pilots could push their aircraft into any attitude, any maneuver, and trust that the motor would respond. British pilots couldn't. They had to half-roll and pull through instead of pushing straight into a dive. It took longer. It gave the enemy time to escape. And it was killing Royal Air Force pilots who couldn't afford the handicap. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. By June 1940, with France collapsing and Britain facing invasion, the problem had become critical. The Battle of France was lost. The Battle of Britain was about to begin. And the Royal Air Force was flying fighters with engines that died when pilots needed them most. The fault lay in the carburetor. The Rolls-Royce Merlin was a magnificent engine, 12 cylinders arranged in a V, supercharged, capable of producing over 1,000 horsepower. It powered the Spitfire, the Hurricane, the Lancaster bomber, dozens of aircraft types. But it used a float carburetor, a design that relied on gravity to keep fuel flowing to the engine. When the aircraft entered negative gravity during a dive, the fuel in the carburetor's float chamber was thrown forward, away from the feed pipe. The mixture became too rich, flooded the engine, and it cut out. Sometimes it restarted when the pilot leveled off. Sometimes it didn't. German pilots knew about this weakness. They exploited it. When a Spitfire or Hurricane got on their tail, they pushed into a steep dive. The British pilot had two choices: try to follow and risk his engine quitting, or half-roll and pull through, losing precious seconds while the German escaped. Either way, the Luftwaffe gained an advantage that had nothing to do with pilot skill or aircraft performance. It was purely mechanical. A carburetor design that couldn't handle negative G-forces. Rolls-Royce engineers knew about the problem. They had known for months. They were working on a solution, a pressure carburetor that would use fuel pressure instead of gravity to feed the engine. But designing, testing, and manufacturing a completely new carburetor would take time. Months. Maybe a year. And Britain didn't have a year. The Germans were preparing Operation Sea Lion, the invasion of Britain. The Luftwaffe was massing aircraft across the Channel. Hermann Göring had promised Hitler he would destroy the Royal Air Force in 4 days. The Battle of Britain was about to begin. And British fighters had engines that died in combat. Into this crisis stepped a 31-year-old woman who had spent her childhood taking apart motorcycles, who had been told repeatedly that engineering was not a profession for women, and who was about to save the Royal Air Force with a piece of brass smaller than a coin. Her name was Beatrice Schilling. Her colleagues called her Tilly. And she was about to prove that sometimes the most elegant solution to a catastrophic problem is also the simplest. Beatrice Schilling was born on March 8, 1909, in Waterlooville, Hampshire. Her father, Henry Schilling, was a butcher. Her mother, Annie, managed the household. The family was working class, respectable, conventional. Nothing about Beatrice's background suggested she would become one of Britain's most important aeronautical engineers. Except that from the age of 5, she was obsessed with how things worked. She spent her pocket money on hand tools. Screwdrivers, wrenches, pliers. She took apart clocks, music boxes, household appliances. She studied how gears meshed, how springs stored energy, how mechanisms translated motion from one form to another. Her parents watched with bemused tolerance as their daughter dismantled and reassembled every mechanical object she could get her hands on. Most of them still worked afterward. Some worked better. At 14, Beatrice bought her first motorcycle. A used two-stroke that needed work. She taught herself to strip the engine down to its components, clean each part, understand how they fit together, rebuild it. The engine ran. She rode that motorcycle for years, maintaining it herself, modifying it, improving it. She entered it in a national meccano construction competition and won. She was the only girl competing. The judges were astonished. Beatrice wasn't. She knew she was good with machines. She knew she understood engines better than most boys her age. What she didn't know yet was whether anyone would let her turn that talent into a career. In 1926, at 17, Beatrice became an apprentice at an electrical contracting firm run by Margaret Partridge, one of the few women in Britain who owned an engineering business. For 2 years, Beatrice learned electrical installation, wiring, circuit design. She wrote articles for The Electrical Age, the magazine of the Electrical Association for Women. One article described how she and another apprentice wired an entire house in 3 days. Another explained how to build a home wireless set from components. Both were aimed at girl guides, encouraging young women to see engineering as something they could do. Margaret Partridge recognized Beatrice's talent. She encouraged her to pursue formal education. In 1929, Beatrice enrolled at the Victoria University of Manchester to study electrical engineering. She was one of only 2 women in the program. The other was Sheila McGuffey. The male students stared. The professors expressed doubt. Engineering was a man's profession. Always had been. Women lacked the mathematical aptitude, the physical strength, the practical mindset. That was the conventional wisdom in 1929. Beatrice ignored it. She completed her bachelor's degree in electrical engineering in 1932, then stayed for another year to earn a Master of Science in mechanical engineering. She graduated with honors. Then came the hard part. Finding a job. Britain was deep in the Great Depression. Engineering firms were laying off workers, not hiring. And they certainly weren't hiring women. Beatrice applied to dozens of companies. She received polite rejections. Some weren't polite. Women don't belong in engineering. Women can't handle the physical demands. Women will quit to get married. The excuses varied. The result was always the same. No. For 2 years, Beatrice worked as a research assistant at the University of Birmingham, assisting Professor G.F. Mucklow with experimental work. It was temporary. It paid poorly, but it kept her in engineering. And in 1936, she received an unexpected opportunity. The Royal Aircraft Establishment at Farnborough was hiring. The RAE was Britain's primary aeronautical research facility, responsible for testing aircraft, developing new technologies, solving technical problems for the Royal Air Force. They needed a technical author, someone who could write clear documentation of complex engineering systems. Beatrice applied. She was qualified. She had the education, the experience, the writing skills from her articles. She was offered the position. She accepted. She started as a technical author. She wrote manuals, specifications, reports. It was office work, clerical, far removed from the hands-on engineering she wanted to do. But she was inside the RAE. She was around aircraft. She was near the workshops, the test cells, the engineers who were actually building and modifying engines. And she watched. She learned. She waited for an opportunity. The opportunity came when she demonstrated that she could do more than write about engineering. She could do engineering. When technical problems arose, Beatrice didn't just document them. She solved them. She could braze copper joints, a skilled welding technique. She could read engineering drawings, spot errors, suggest improvements. She could work with her hands as well as any man in the facility. Better than some. The workshop staff noticed. The engineers noticed. And on November 1, 1939, 2 months after Britain declared war on Germany, Beatrice Schilling was promoted. She was transferred from technical writing to hands-on research. Her new role, carburetor development and testing. She would lead a small team investigating fuel system problems in aircraft engines. It was exactly what she had wanted. And the timing was perfect. Because in 6 months, British fighter pilots would be dying because of a carburetor flaw that nobody had been able to fix. The problem with the Merlin engine's carburetor wasn't new. Test pilots had reported it for years. During aerobatic maneuvers, during combat training, the engine would cut out under -G. Rolls-Royce knew. The Air Ministry knew. But during peacetime, it hadn't been considered urgent. Pilots learned to work around it. They avoided certain maneuvers. They half-rolled instead of diving straight. It was an inconvenience, not a crisis. Then came war. Then came combat. Then came German fighters that didn't have the problem. And suddenly the carburetor flaw was killing pilots. The technical explanation was straightforward. The Merlin used an SU float carburetor. Fuel from the aircraft's tank flowed into a float chamber. As fuel entered, a float rose. When the float reached a certain level, it closed a valve, stopping the flow. This maintained a constant fuel level in the chamber. From there, fuel was drawn through jets into the venturi, where it mixed with air and flowed to the cylinders. The system worked perfectly under positive or neutral G-forces. Gravity kept the fuel in the bottom of the float chamber, near the feed pipe. But under -G, gravity reversed. The fuel in the float chamber was thrown upward, away from the feed pipe. The float dropped. The valve opened. More fuel rushed in. The mixture became too rich. The engine flooded and stopped. Sometimes the pilot could restart it by leveling off and waiting for the fuel to settle. Sometimes the aircraft was too low, or the situation too urgent, and the pilot crashed. Or was shot down while his engine was dead. Rolls-Royce's solution was to develop an entirely new carburetor. A pressure carburetor that would pump fuel under pressure instead of relying on gravity. It was the correct long-term solution. It would eliminate the problem completely. But it required designing new components, testing them, setting up production lines, manufacturing thousands of units, installing them in aircraft. The timeline was 18 months. Minimum. The Battle of Britain would be decided in weeks. Beatrice Schilling looked at the problem differently. She wasn't interested in the perfect solution. She was interested in a solution that could be implemented immediately. Something simple. Something that could be installed in operational aircraft without pulling them out of service. Something that would work well enough to give British pilots a fighting chance. She studied the test data. Engine cutouts occurred during -G maneuvers when the carburetor flooded with excess fuel. The problem wasn't lack of fuel. It was too much fuel entering too quickly. What if she restricted the fuel flow? Not enough to starve the engine under normal operation, but enough to prevent flooding during a dive? The idea was almost too simple. A small metal disc with a precisely sized hole in the center. Install it in the fuel line between the fuel pump and the carburetor. Under normal operation, enough fuel would flow through the hole to keep the engine running at full power. But during -G, when fuel tried to flood the carburetor, the restrictor would limit the maximum flow rate. The engine would continue receiving fuel, just not enough to flood and quit. The concept was simple. The execution required precision. The hole had to be exactly the right size. Too large, and it wouldn't prevent flooding. Too small, and it would restrict fuel flow even under normal conditions, reducing engine power. Beatrice calculated the optimal diameter. She fabricated a prototype. A brass disc, small enough to fit in her palm, with a hole drilled to within a few thousandths of an inch of the calculated dimension. She tested it. The RAE had engine test cells, concrete bunkers where Merlin engines could be run at full power while instrumentation measured every parameter. Temperature, pressure, fuel flow, power output. Beatrice installed her restrictor in a test engine. The technicians mounted the engine in the test cell, connected the fuel lines, the cooling system, the exhaust. They ran the engine through its normal operating range. Full power, cruise power, idle. The restrictor made no difference. The engine performed exactly as it should. Then they simulated -G. They tipped the fuel system to replicate the forces of a dive. Without the restrictor, the carburetor flooded. Fuel mixture went rich. The engine coughed, sputtered, died. With the restrictor installed, the engine kept running. The fuel flow was limited. The mixture stayed lean enough. The power dropped slightly under extreme -G, but the engine didn't quit. It worked. Beatrice refined the design. She simplified it from a brass thimble to a simple flat washer. Easier to manufacture. Easier to install. By March 1941, she had a solution ready for operational use. A brass washer with a precisely drilled hole that could be welded into an aircraft's fuel line in minutes without removing the engine. Now she needed to get it into the aircraft that needed it most. The Spitfires and Hurricanes of fighter command. The aircraft that were, at that very moment, defending Britain against the Luftwaffe. Beatrice Schilling loaded her tools and a box of restrictors onto her motorcycle. Not a standard-issue staff car. Her personal motorcycle, a powerful machine she had been racing at Brooklands Circuit before the war. She was one of only 3 women to earn the British Motorcycle Racing Club Gold Star for lapping Brooklands at over 100 miles per hour. She knew how to ride. And in March 1941, she rode that motorcycle from one RAF fighter station to another across southern England, installing her modification personally. She arrived at each base unannounced. A woman in coveralls, riding a motorcycle, carrying tools and a box of brass washers. The ground crews stared. The pilots were skeptical. Who was this woman claiming she could fix a problem that Rolls-Royce's best engineers hadn't solved? Beatrice didn't argue. She showed them. She demonstrated the installation. Drain some fuel from the line. Weld the restrictor in place. Refill the system. Test the engine. 10 minutes per aircraft. The pilots flew test flights. They pushed into dives, pulled -G, tried to make the engine quit. It didn't quit. The power dropped slightly during extreme negative maneuvers, but the engine kept running. They could dive on German fighters without their engine cutting out. They could pursue. They could attack. For the first time since the war began, British pilots could fight without one hand tied behind their backs. Word spread. Squadron commanders requested the modification. More ground crews learned to install it. By the end of March 1941, hundreds of Spitfires and Hurricanes had been fitted with what the pilots were calling Miss Schilling's orifice. By the time the Battle of Britain's most intense phase ended in October 1941, nearly every frontline RAF fighter had the restrictor installed. The impact was immediate and measurable. RAF pilots reported successful pursuit attacks that would have been impossible before. German pilots noticed British fighters diving more aggressively. The Luftwaffe's tactical advantage from -G maneuvers disappeared. And Beatrice Schilling's simple brass washer became one of the most important technical modifications of the war. Sir Stanley Hooker, the Rolls-Royce engineer who led supercharger development, coined the term Miss Schilling's orifice. It stuck. The phrase was simultaneously respectful and slightly ribald, very British, very RAF. Beatrice didn't object. She had saved lives. She had solved a problem that nobody else had solved. And she had done it with a piece of brass that cost almost nothing and could be installed by any competent mechanic in minutes. The restrictor wasn't perfect. Beatrice knew that. Rolls-Royce knew that. The pilots knew that. Under extreme -G forces, engine power still dropped by about 10 to 15%. The brass washer limited fuel flow, which meant it limited maximum power during inverted flight or steep dives. But the engine didn't quit. And in combat, an engine running at 85% power was infinitely better than an engine that had stopped completely. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The restrictor was always intended as a temporary solution. A stopgap. Something to keep pilots alive while Rolls-Royce developed the proper fix. The proper fix was the Bendix-Stromberg pressure carburetor, licensed from the Americans and adapted for the Merlin engine. It used fuel pressure instead of gravity. It could operate at any angle, any G-force, positive or negative. It maintained perfect fuel mixture under all conditions. It was everything the float carburetor wasn't. And it wouldn't be ready until 1943. For 2 years, from March 1941 until the pressure carburetors entered production in mid-1943, Miss Schilling's orifice was the only thing standing between RAF pilots and engine failure during combat maneuvers. During that period, the restrictor was installed in thousands of aircraft. Spitfires, Hurricanes, later marks of the Lancaster bomber, Mosquito fighter bombers, every aircraft that used the Merlin engine and might encounter combat situations requiring negative G maneuvers. Beatrice continued her work at the Royal Aircraft Establishment throughout the war. The carburetor restrictor made her famous within aviation circles, but it was just one project among many. She worked on fuel system improvements, engine testing procedures, performance analysis. She was promoted to Principal Technical Officer. She led teams of engineers, most of them men, all of them willing to work under her direction because she was simply better at solving technical problems than anyone else available. She encountered discrimination constantly. Some of it was petty. The Ray's senior mess, the club and dining hall for senior staff, prohibited women from entering. Beatrice was a senior technical officer. She had earned the rank. She couldn't use the facilities that came with it because she was female. British law prohibited women from working night shifts in factories. Beatrice needed to run engine tests at night when test cells were available. She ignored the law. Her supervisors pretended not to notice. One RAE chief engineer refused to allow women to enter his building. Beatrice needed to inspect equipment in that building. She entered anyway. The chief engineer complained to senior management. Senior management sided with Beatrice. Her work was too valuable to obstruct over antiquated prejudices about women in engineering spaces. The most visible discrimination came from the honors system. In 1949, 4 years after the war ended, Beatrice Schilling was appointed an officer of the Order of the British Empire. The OBE is a significant honor, recognition of exceptional service to the nation. But it's not the highest honor. Men who had made contributions similar to Beatrice's carburetor restrictor had received knighthoods, commander-level appointments, higher recognition. Beatrice received the OBE. Many observers noted the disparity. A woman who had arguably saved hundreds of RAF pilots' lives received less recognition than men whose contributions were less immediately life-saving. Beatrice didn't complain publicly. She accepted the OBE. She continued her work. After the war, she shifted focus to new technologies. Britain was developing ballistic missiles. The Blue Streak missile program needed engineers who understood propulsion systems, fuel flow, engine performance under extreme conditions. Beatrice joined the team. She applied the same methodical problem-solving approach she had used on the Merlin carburetor to rocket engines operating under entirely different principles. She also researched runway safety. Specifically, how wet runways affected braking performance. Aircraft were getting heavier, faster. Jet engines were replacing propeller engines. Landing speeds were increasing. Runways that had been adequate in 1940 were marginal by 1955. When it rained, they became dangerous. Beatrice studied the physics of tires on wet pavement, the hydroplaning effect, the relationship between water depth, tire design, and braking distance. Her research contributed to new runway surface specifications, drainage requirements, safety procedures that are still in use today. She helped design a bobsled for the Royal Air Force's Olympic team. The project had nothing to do with aircraft. The RAF wanted to compete in the Winter Olympics. They needed a well-designed bobsled. Beatrice understood aerodynamics, materials, structural engineering. She designed a sled that was fast and safe. The RAF team used it in competition. Throughout her career, Beatrice maintained her passion for motorcycle racing and sports car competition. Before the war, she had raced motorcycles at Brooklands, earning her gold star by lapping at over 100 miles per hour. After the war, she raced sports cars at Goodwood Circuit. She competed in members' meetings, scored podium finishes, drove with the same precision and calculated aggression she brought to engineering problems. In 1967, American Formula One driver and team owner Dan Gurney contacted Beatrice. His Eagle Mark I racing car had an overheating problem. Multiple engineers had tried to solve it. None had succeeded. Gurney had heard about Beatrice Schilling. He asked if she would take a look. She did. She identified the problem. She recommended modifications. The overheating stopped. Gurney's car became competitive again. In 1956, Beatrice joined the Institution of Mechanical Engineers using her married name, Naylor. She had married George Naylor, a fellow engineer, in 1948. She kept her maiden name for professional purposes but used her married name for official registrations. The institution elected her as an associate member, allowing her to use the designation CENG, Chartered Engineer, after her name. In her application, she outlined her contributions to aeronautical engineering, including the RAE restrictor. The institution recognized the significance of her work. The University of Surrey awarded Beatrice an honorary doctorate in 1969. She was 70 years old, still working at the RAE, still solving problems, still proving that gender had nothing to do with engineering capability. The honorary doctorate acknowledged what many in the engineering community had known for decades. Beatrice Schilling was one of Britain's most important aeronautical engineers. Her work had saved lives. Her innovations had contributed to Allied victory in World War II. And she had done it all while facing barriers that male engineers never encountered. Beatrice retired from the Royal Aircraft Establishment in 1969, the same year she received her honorary doctorate. She had worked there for 33 years. She had contributed to dozens of projects, solved hundreds of technical problems, mentored younger engineers, published research papers, advanced the state of aeronautical engineering in Britain and beyond. She died on November 18, 1990, at the age of 81. By then, the Merlin engine had been retired for decades. The Spitfires and Hurricanes that had defended Britain in 1940 were museum pieces, preserved artifacts of a desperate time. The brass restrictors that Beatrice had installed in those aircraft were long gone, replaced by modern fuel injection systems that didn't need such crude solutions. But the principle remained. The idea that sometimes the most elegant engineering solution is also the simplest. That a massive problem doesn't always require a massive solution. That a small brass washer, precisely designed and correctly placed, can save more lives than a complex system that takes years to develop. The story of Miss Schilling's orifice matters because it reveals how innovation actually happens. Not always in corporate research labs with unlimited budgets. Not always through committees and formal development programs. Sometimes through one person who understands a problem deeply enough to see a simple solution that everyone else missed. Rolls-Royce had brilliant engineers. They were developing the pressure carburetor. It was the correct long-term solution. But it would take 18 months. Beatrice saw that 18 months was too long. She saw that pilots were dying now. She saw that they needed something immediately. And she delivered it. The restrictor worked because Beatrice understood exactly what the problem was. Not engine failure in general. Not carburetor design in general. Specifically, fuel flooding during negative G maneuvers. Once she understood the specific problem, the solution became obvious. Limit fuel flow. Not eliminate it. Not redesign the entire system. Just limit maximum flow rate to prevent flooding. The genius wasn't in the brass washer itself. Anyone could make a brass washer. The genius was in recognizing that a brass washer was the correct solution. In calculating the exact hole diameter that would prevent flooding without restricting normal fuel flow. In understanding that good enough now was better than perfect later. In personally traveling to fighter stations to install the modification herself because she knew that demonstration was more convincing than explanation. RAF pilots in 1941 didn't know Beatrice Schilling's background. They didn't know she had been racing motorcycles at Brooklands before the war. They didn't know she had a master's degree in mechanical engineering from Manchester. They didn't know she had spent years working on carburetor development at the RAE. They just knew that a woman had shown up on a motorcycle with a box of brass washers and had fixed a problem that had been killing their friends. Some of them initially doubted. A woman engineer was unusual. A woman claiming to have solved a problem that Rolls-Royce hadn't solved seemed impossible. But the test flights proved it. The engine kept running during dives. Pilots who had been avoiding negative G maneuvers could now pursue German aircraft aggressively. The tactical disadvantage disappeared. By mid-1941, German intelligence reports noted that British fighters were diving more confidently. Luftwaffe pilots reported that Spitfires and Hurricanes were no longer breaking off attacks during steep dives. The German tactical advantage from fuel injection was gone. British fighters could maneuver equally well. And the Germans never knew why. They never knew that the change was due to a simple brass washer installed by a woman on a motorcycle. The restrictor remained in use until the pressure carburetors became available in 1943. Some aircraft kept the restrictor even after pressure carburetors were available. If the aircraft wasn't scheduled for a major overhaul, if it was needed for operations, if the restrictor was working adequately, maintenance crews left it alone. Don't fix what isn't broken. Some Merlin engines flew the entire war with Miss Schilling's orifice still installed. After the war, when historians studied the Battle of Britain, they focused on the usual factors. The courage of the pilots. The skill of the commanders. The effectiveness of radar. The production capacity of British aircraft factories. The strategic mistakes of the Luftwaffe. All of those factors mattered. But few historians mentioned that British fighters had a critical technical flaw that was fixed midway through the battle by a woman engineer with a brass washer. The story was too small, too technical, too undramatic. Except it wasn't undramatic at all. Every pilot who dove on a German aircraft after March 1941 benefited from Beatrice's work. Every successful interception that required a steep dive was made possible by that brass restrictor. Every German bomber shot down by a Spitfire or Hurricane that would have escaped 6 months earlier represented lives saved. British lives on the ground who weren't killed by bombs. Allied merchant seamen who weren't torpedoed by U-boats that would have been protected by Luftwaffe air cover if Britain had fallen. American soldiers who landed at Normandy instead of fighting a war against a Nazi-dominated Europe that controlled the Atlantic. The counterfactual is impossible to calculate precisely. But the RAF's official assessment was clear. The carburetor problem was serious enough to significantly reduce fighter effectiveness. The restrictor eliminated the problem quickly enough to matter during the critical period of the Battle of Britain. And the long-term solution, the pressure carburetor, wouldn't have been available in time to affect the outcome. Beatrice Schilling saved the program. She bought time. 18 months of time. And during those 18 months, Britain survived. The Luftwaffe failed to achieve air superiority. Operation Sea Lion was cancelled. And Nazi Germany lost its best chance to knock Britain out of the war. One woman. One brass washer. One simple idea executed perfectly at exactly the right moment. The lesson isn't that complex engineering is unnecessary. The pressure carburetor was better than the restrictor. It provided more power under all conditions. It eliminated the problem completely instead of mitigating it. Rolls-Royce was right to develop it. But the pressure carburetor took time. And time was the one resource Britain didn't have in 1941. The lesson is that solving problems requires understanding them deeply enough to know which solution is appropriate for the circumstances. Not the best possible solution in the abstract. The best solution available right now with the resources at hand and the time available. Beatrice understood that. She wasn't trying to win an engineering award. She was trying to keep pilots alive. And she succeeded. Her story also reveals the absurdity of the barriers women faced in technical fields. Beatrice had to fight for every opportunity. She had to be better than male engineers to receive equal recognition. She had to ignore discrimination, work around regulations that didn't make sense, prove herself repeatedly in ways that men never had to. And even after saving hundreds of lives with an innovation that became standard on thousands of aircraft, she received less official recognition than male engineers whose contributions were less significant. The OBE she received in 1949 was an honor. But it wasn't proportional to the impact of her work. Other engineers who worked on the Merlin engine received higher honors. Some received knighthoods. Some received commander-level OBEs or CBEs, which rank higher than officer. Beatrice received the OBE. The disparity was noted at the time. It was criticized. Nothing changed. The honors system reflected the prejudices of the era. Women could contribute. They could excel. But they would not receive equal recognition. Beatrice apparently didn't let it bother her. Or if it did, she didn't complain publicly. She continued working. She continued solving problems. She continued racing motorcycles and sports cars. She continued mentoring younger engineers, including women who were entering the field because Beatrice had proven it was possible. By the 1960s and 70s, more women were studying engineering. The University of Manchester, where Beatrice had been one of 2 women in the electrical engineering program in 1929, had dozens of female engineering students by 1970. The barriers were dropping. Slowly, but dropping. And every woman who graduated with an engineering degree owed something to the women like Beatrice who had gone first, who had proven that women could engineer as well as men, who had refused to accept that gender determined capability. Today, Beatrice Schilling is remembered primarily for the restrictor, Miss Schilling's orifice. The phrase itself is memorable, slightly naughty, very British. It's appeared in books about the Battle of Britain, documentaries about World War II aviation, engineering history courses. The University of Manchester celebrates her as one of their distinguished alumni. The Royal Aeronautical Society recognizes her contributions. Children's books have been written about her. The Girl Who Could Fix Anything by Mara Rockcliffe tells her story for young readers interested in science and engineering. But the restrictor was just one innovation in a long career. Beatrice worked on aircraft engines for 33 years. She contributed to missile development, runway safety research, Olympic bobsled design, Formula One racing car engineering. She published papers, mentored engineers, advanced the field. The restrictor made her famous because it had immediate, visible impact during a critical historical moment. But it wasn't her only achievement. It was just the most dramatic. The real achievement was simpler and more profound. Beatrice Schilling proved that women could be world-class engineers. That gender had nothing to do with the ability to understand complex mechanical systems, identify problems, develop solutions, implement fixes. That the barriers women faced in technical fields were artificial, cultural, changeable. She didn't prove it by arguing. She proved it by doing. She fixed a problem that nobody else had fixed. She saved lives that nobody else had saved. And she did it with a brass washer that cost almost nothing but required understanding that was priceless. Up next, you've got 2 more standout stories right on your screen. If this one hits the mark, you won't want to pass these up. Just click and check them out. And don't forget to like, subscribe and turn on the notification bell so you don't miss any upload from us.